Hi everyone, welcome to the lecture on naive classifiers. So far we have looked into probabilistic learning. We have also looked into generative and discriminative models. So today we will look into one of the generative models, which is naive classifier. So where are we? We have seen Bayesian learning. We have seen how it can be used for a probabilistic criterion to select a hypothesis. We have also seen that how we can use maximum a posteriori learning and maximum likelihood learning, which is a special case of the former. And we also learn functions that predict probabilities of outcomes, different from using a probabilistic criterion to learn. So now we will look into maximum a posteriori prediction as opposed to MAP learning. So the key difference here is that we have seen MAP learning, but we are going to see MAP prediction. So let's quickly rewind and see what is MAP learning. So here it is nothing but we are maximizing the likelihood and prior for P of H given D, that is the likelihood of a hypothesis where that hypothesis belongs to a hypothesis space, and we have to maximize the likelihood or maximize the posterior given a data set, and it is manifested as seen in this expression written as H map. Anyway, now let's look into MAP prediction. So here, so if you see what is the difference, the main difference is that in MAP learning, we were talking about hypothesis which comes from a hypothesis space and the data set. Or in other words, we were talking about the random variable y being a hypothesis, the random variable x being the data set. Here, we are talking about prediction. So our y, the random variable y is a label and x is an input, not the whole data set, but an input. Now, please note that this is represented as a vector or a sequence or a combination of features. Hence, we use the boldface here. So the base rule is still the same. If you go back and see, the base rule was for random variables y and x. During MAP learning, we considered y to be the hypothesis, d to be the data set. Here, in MAP prediction, y is the label and x is the input or a feature combination. So using the base rule for predicting a label y for a given input x, we will write it as p of y equal to y, x equal to x, where the notations in the capital letter y and x are the random variables, and small y and small x, which is in boldface, are your label and input respectively. So we know that again, how do we write that when we have to maximize the likelihood for a label? We ignore the denominator, which has nothing to do with which is not described over which is not defined over the random variable y. So we come up with p of x equal to x given y equal to y into p of y equal to y. So this is the prior, this is the likelihood. Everything remains same, only thing is that the random variables have changed. And naturally the purpose or the outcome is also changing. Yes, so we have already discussed that this is the likelihood, this is the prior. So what exactly is the likelihood here? It is the likelihood of observing this input x when the label is y. The prior is the probability of the label being y. Now, all we need are two sets of probabilities, but it might be a bit difficult to visualize or to think through how does this apply in a day-to-day scenario. So let's take a toy problem. It's a day-to-day scenario. I wouldn't say it's a real-world scenario, but it's still a day-to-day thing that we do. It may not be a true real-world application, but it's still a real-world scenario. Let me correct that. It's a real-world scenario, but need not be a real-world application. So let's see what is that. So let us say we are all in the same location and we want to go out and play tennis in that location. So how do we compute whether today is a good day, or any day, any given day is a good day to go and play tennis? So without any other information, we will first see what is the prior probability that we should play tennis. And that is shown here. So this is the prior, the smaller rectangle here, or as P of y equal to y, where we have a binary possibility for the labels, right? We either play tennis or we don't play tennis. So it's a yes or no, where yes being we will play tennis, no being we will not play tennis. And the probabilities are 0.3 and 0.7 because the probability have to add up to 1. So, and there are only two labels. So it's 0.3 and 0.7. Now, this is the prior. We have not considered any other factors that will help us decide this. This has been something we have observed that generally people don't go for playing tennis, as against 30% of the time people go for playing tennis. So that is why there is a likelihood. It's defined. We are not questioning how that is arrived at. We are just taking it at its face value, or axiomatically we are taking it. Now, let's say on the days that we do play tennis, what is the probability that the temperature is T and W? Now, what does that even mean? So what we are talking about is that when we decide to go and play tennis, we often take few factors into consideration. And these factors are what we represent as the features for the day. Now, to play tennis, we have decided that we will take two features. One is the temperature, another is the wind. And it further can be seen that there are only two possible values for both temperature and wind. Temperature can either be hot or cold, right? So temperature is either hot or cold. Wind is either strong or weak. So now this is how we do this likelihood thing, because we want to predict whether we should play tennis given the temperature and wind for a day. To do that, we first have to calculate the prior and the likelihood. And what is likelihood? Likelihood is the probability of x given y. So we are calculating that. So let us say the y that is playing tennis is yes. So the y is given and we assume that the y value is yes or y value is 1. Then we know the likelihood of x, where x is a combination of multiple features, in this case 2 features. Now what are those features? It is when it is hot and strong, that is temperature is hot, wind is strong, we have 0.15. When it is hot and weak, it's 0.45. Similarly, we have the values whenever we are playing tennis. Now, whenever we are not playing tennis, that is when the value of the label tennis is equal to no, or play tennis is equal to no, we again find the P of x given y. So for every combination of label and features, or every sequence of label and features, we are calculating the likelihood and we have a bunch of values. So altogether there are 4 combinations because we have 2 features, and that 4 times 2 is there because we have 2 labels. So we have total of 8 different values to consider during the likelihood. Now let's say that the temperature is hot and the wind is weak. Okay. Shall we play tennis? So using the MAP prediction, we get the probabilities for play tennis and not play tennis. Okay. So it is play tennis, that's why it's 0.3, and when it is hot and weak and the tennis equal to yes is 0.4, so that is 0.4 into 0.3, 0.12. Now not playing tennis is 0.7, so the prior is here, but when the temperature is hot and the wind is weak, hot, weak, the probability here is 0.1, so 0.1. So 0.1 into 0.7, 0.07. So here, as per MAP prediction, the likelihood of playing tennis is higher, or the posterior for playing tennis is higher than not playing tennis. So we say that we should, or the map prediction says that we should play tennis. Yeah. So this is how we generally estimate this. So essentially we need to learn the prior and the likelihood, which is P of y and P of x given y. Now, how hard is it to learn such probabilistic models? Don't you think that what we have done is something that we could do it in a single sheet of paper? So have we solved machine learning by using a single sheet of paper? Do we really need to have such elaborate setups? So far we have seen that everything is straightforward and we can just manually do it on a single sheet of paper. We just need to learn the prior and the likelihood, right? Now let's look at the complexity here. Now prior is a single number. However, if we look at the likelihood, we can see that our input contains 4 features. And the 3 of these features take 3 values each, and the remaining one takes 2 values. So now I am probably talking about the same problem, that is play tennis, but I have increased the number of features from 2 to 4. So previously we had 2 features, each of them having 2 values, and we have 2 values for the label. So the 2 values for the label remain the same, but the likelihood now has 4 features, of which you can see that 3 of them have 3 values each and 1 of them have 1 value. There's 2 values, sorry. So now the number of assignments, or the number of parameters to consider, are 3 into 3 into 3 into 2 minus 1. So 1 each for each feature and minus 1. So that will be 3 into 3 is 9, 9 3 is 27, 27 2 is 54, 53. So from 3 to 53, right? So previously we had, if you go by the same logic, it's 2 into 2 minus 1, so it's 3. Now it is 53. So 53 parameters, 1 for each assignment. So if I have to generalize and state it, then we can say that if there are k labels, then for computing the prior p, I need k minus 1 parameters. So that's why previously we had, when we had 2 values or 2 labels, we are having 1 parameter. Here there is k minus 1. Then if there are k labels, then k minus 2 parameters are required for the prior. Sorry, k minus 1 is required for the prior. Now let's again simplify things and let's assume that we have Boolean features. If we have Boolean features, then the value for each possible assignment for each y becomes k times 2 power d minus 1. So now it's okay to have a lot of parameters, but what is the challenge? The challenge is that as the number of parameters increase, we need a lot more data to estimate these numbers. As the number of parameters increase, we have to estimate all of those. To sufficiently get data or to sufficiently get enough information, we need to go through a lot of data, and this data requirement increases. Now this leads to high model complexity, and if we have limited data, then there is high variance in the parameters. So this is a challenge we have to be mindful of. Now, how can we deal with this complexity? A simple solution here is to make independence assumptions. Now, why is it so? So we can make independence assumptions. Independence assumptions. So independence between what? Independence between features. So if we see here, we have seen that k into 2 power d minus 1, that has come up due to the combinatorial explosion of the features. So when we take a combination of features, that leads to combinatorial explosion in number of parameters. Instead, if we assume independence, the number of parameters are substantially reduced. So what is conditional independence? Let's have a look at it. Suppose x, y, and z are random variables. Then x is conditionally independent of y given z if the probability distribution of x is independent of the value y when z is observed. So p of x given y comma z is p of x given z, or p of x given c, p of y given c. Now in this case, so for a given input, we represent it as a combination of feature values, and this combination led to k times 2 power d minus 1 parameters. Now what if all the features were conditionally independent given the label? Then I can decompose and write it as the following: x1 given y, x2 given y, xd given y, so modeling the features. So for a given input, we represent it as a combination of values for a fixed set of features. And this combination led to k times 2 power d minus 1 parameters. Now what if all the features were conditionally independent given the label? That is, p of x1, x2, x3 up to xd given y can be represented as p of x1 given y, x2 given y up to xd given y. Now we only require d numbers for each label, or kd parameters overall, instead of k into 2 power d minus 1. And we call this assumption as the naive assumption or the naive Bayes assumption, and hence this is the basis for the naive Bayes classifier. So in a naive Bayes classifier, the features are conditionally independent given the label y. So to predict, we need again two sets of probabilities, the prior p of y, and for now each feature we have to estimate the likelihood p of xj given y. So we don't have to do them jointly. We don't care about like the combination of features or the impact of the combination of features. We only are interested in p of xj given y. So here you have to bear in mind that this is an assumption we are making, that couple of features or combination of features is not giving any additional information than the individual features. Now this need not be a real world assumption. There can be a lot of scenarios where we can say the sum of the parts is more than the whole is more than the sum of the parts. So sometimes the combination of features can give you some extra information that individual feature can't give you, but we are only assuming this for the sake of simplifying the computation, and we are going to apply it only on those scenarios where this is more or less applicable, or the loss due to that assumption is manageable. So this is not something that we can apply everywhere, but this is something very interesting that in spite of being in existence for so long and in spite of like having so much advanced methods, this one is really effective. It's very difficult to beat this neighbor's approach when you start figuring out a problem, and when you come up with a complex problem. It's often the case that this neighbors can be a good baseline or a good competitor to that approach. Anyway, so what we are trying to say here is that, again, Bayes rule. So P of y given x can be applied here, or it's basically the argmax of y of P of y, P of x1, x2, xd to y given y. Now we said conditional independence, so we are representing it as a product of each individual features given the label y, given y. So the likelihood is the product of each feature given the label. Now, what is the decision boundary of name Bayes? Consider a binary classification scenario with two classes, positive and negative. We predict the label to be positive if the posterior likelihood for the positive, is higher, then we say that the label to be positive. So it is the final, this is illustrated here. Now, how do we go about learning the naive-Bayes classifier? So what is the hypothesis function H defined by? It's a collection of probabilities where we have prior for each label P of y, likelihood for feature xj, for every feature basically, given a label y, P of xj given y. This has to be a subscript. Now, if we have a dataset D with xi, yi with m examples, and we want to learn the classifier in a probabilistic way, what is the probabilistic criterion to select the hypothesis? So no surprise there, it is, we will perform maximum likelihood estimation, because again we assume the prior to be uniform. Now here H is defined by all the probabilities used to construct the naive Bayes. So since each example is independent and identically distributed, we can formulate the maximum likelihood hypothesis HML to be shown as here. So it's the product of probability of xi, yi, which is a data point, given the hypothesis H, and we have to maximize the H. So in other words, what we are trying to say here is that this particular term, which is for a single data point, and we have m data points in D, and it asks what probability would this particular H assign to the pair xi, yi. Please note that xi is boldface to indicate that it is not a scalar, rather a vector representation, implying a combination or a sequence of feature values. Now, using the naive-Bayes assumption, I can rewrite the highlighted portion here into what we see in the third line. Essentially, each feature j is independent of other features, and hence a product of conditional probability of each feature suffices. And now, how do we proceed? So we have already seen this in the case of logistic regression. For computational efficiency, we convert the products to summation by taking the logs. So the products becomes the summation, and you can see the logs as well. So now what next? We need to make a modeling assumption about the functional form of these probability distributions, because it's a generative model. We are estimating the input structure as well as the decision boundary. So we need to have a modeling assumption about the functional form of these probability distributions. So for simplicity, let's assume there are only two labels, 1 and 0, and all the features are binary. Now let's say the prior of the probability y equal to 1 is p, which is written in blue here. So naturally, since there are only two labels, p of the probability of y equal to 0 is 1 minus p, as there are only two labels. So the prior probability is from the Bernoulli distribution. Similarly, likelihood for each feature given a label can be written as follows. Let's say the likelihood for a feature j to be 1 when y equal to 1 and y equal to 0 are aj and bj respectively. Then the likelihood for that feature to be 0 would be 1 minus aj and 1 minus bj. Now we can write the prior p as p of yi given h equals p raised yi equals 1 and 1 minus p raised yi equals 0. So here you may observe a square bracket, and we call it as the Iverson bracket. Its value is 1 if the argument that it encloses is true. In this case, p of, when we say it's yi equal to 1 or yi equal to 0, right? So its value is 1 if the argument is true and 0 otherwise. Similarly, we obtain the expression for the likelihood as well. So previously we obtained the expression for the prior. We have obtained it for the likelihood as well. So we had the variables p, the probability value for the label being 1 and 0, or 1 actually. 1 minus p is the value for being 0. And for each feature j, we had the probability values aj and bj depending on the value of the label. Now these values can be computed as shown here. So summarily, regarding learning in naive Bayes, we can count how often features occurs with each label, normalize them to get the likelihoods. Priors from fraction of examples with each label, and it can be generalized to multi-class. Now finally, for prediction, we use learned probabilities to find highest scoring label. So that's the session on naive Bayes. So now in the next lecture, we will look into naive Bayes versus logistic regression and their similarities as well. After that, we will go for other classifiers. So thanks for attending this lecture. Bye.